Okay, hello everyone. Okay, so basically today's lesson will be the last lecture. All right, and there's nothing else next week. All right, so today basically we have already covered all the material. Okay, that we need to cover for this module. All right, so in the first half we covered all the MIPS and processor architecture and all these concepts. All right, and in this second half, we're going to be looking at we looked at the RTOS, okay, I mean the operating systems and the concept of interrupts and how we can design multi-threaded applications, okay, to fulfill certain objectives. Of course, what we tried on was a sort of software-based system, all right. You can also bring this idea to hardware. Uh, that means you can bring it to an embedded sort of system where you can run an operating system on it and make it do certain specific tasks. All right, so that is of course something also fun to do, but you need a lot of hardware related setup and configuration to be done before that can be sort of fulfilled. Okay, so the micro C OS tree that we ran. Okay, so if you were to deal with OS based systems, generally you will see that the OS has to be what you call ported to different hardware architectures. Okay, so if you go to the micro C OS website and you say you want to download their OS, okay, they will have different sort of OS kernel build for different hardware architecture. Okay, so if you want to run micro C OS tree on, like in our case, Windows based system, okay, they have one build for that. If you want to run it on, let's say, an embedded board that is running on the ARM processor, then you have a separate build for different types of ARM architectures and so on. So it is quite versatile. And the good part is, of course, once you learn, I mean, now that you've learned all these concepts of how to design multi-threaded applications, you can actually bring that uh, and port it over to different platforms. Okay, I mean, in the future, if you were to work with other OS, generally most of them, I would say, have similar frameworks. That means the idea of what a mutex is, semaphore, message queues, task queues, event flags, and so on. So generally, almost all of them have very similar sort of architecture in place, but the low-level details can be different, okay, in terms of when they will switch tasks, all right, when it goes to block, when it goes to ready, and things like that. So some of this underlying behavior might be a bit different when you move from one OS to another OS, but the general architecture and how you design your code base will still be the same. Okay, so in the last week's class, we wrapped up with the cache topic. So today we are just going to have a short tutorial on that. Okay, so let me share screen and then we'll go through the questions. Okay, so basically this is the question that you have. Two questions. Okay, one is to sort of understand how the cache works. All right, very similar to our tutorial. All right, I mean very similar to our lecture slides. All right, but we're just going to have an idea of how to apply it now. Okay, so if you have not sort of gone through the lecture material, then it might still be a bit hazy for you. But I think once you go through and you reference that back with this example, then I think it'll be easier for you to understand. Okay, so in this question here, so we have two questions. In this question one, we are given that we have this machine with a word size of 16 bits. So generally when we say a word, it is architecture dependent. So it could be 16 bits, it could be 32 bits and so on. So in this particular example, we are saying that you have a word size of 16 bits, okay, and address width of 32 bits. All right, so what does this tell? That means in this system, the address bus is 32 bits and the data bus is 16 bits. All right, and we are now designing a direct map, or we have a direct map cache with 16 blocks. All right, and a block size of 2 words. So now let's look at the information that we have. So we have a cache with 16 blocks and a block size of 2 words. So what does that mean? Okay, so when you say 16 blocks, it means 16 cache lines. Okay, one block is considered one cache line. So when you say you have 16 blocks, you have 16 cache lines. Okay, that means one cache line. Okay, this is cache line 0. Okay, 1. Okay, all the way to 15. So you have 15 cache lines. Okay, that is 16 cache lines, 0 to 15. So that is basically what you call the 16 blocks. Okay, this one over here. Now, the next information we have is the block size is 2 words. That means within each cache line, okay, within each cache line, you are storing 2 words. Okay, so I can actually break this up and say that this is word 0 and word 1. Okay, within each cache line is 2 words. And since we know that each word is 16 bits, so this is 16 bits, this is 16 bits, so the total here is 32 bits in one cache line, and I have a total of 16 cache lines. Okay, so that is the first level analysis of extracting how the cache looks like. Okay, based on the description. Now, so now we know how the cache looks like. Let's relate back to the bits, okay, that are going to be mapped to the cache. So the first thing is we know that we have 16 or in each cache line. In each cache line, we know we have 32 bits. Correct? You have 32 bits. So this is one cache line. So in one cache line, I have 2 words. That is 2 times 16, which is 32. Okay, 32 bits, which is equivalent to 4 bytes. All right, so if you recall the cache mapping, okay, the cache mapping, basically, I need to break up my address. So when the address goes out on the address bus, I will break it up into the byte offset, the tag line or cache line, and the rest of it is the what you call the tag. Okay, so you have the byte offset, sorry, cache line and the tag. So the last few bits is what we call the byte offset, which tells us which byte we are looking for within that particular address range. So in this case, since I have 4 bytes, okay, in one cache line I have 4 bytes. So 2 to the power of 2 will give me 4. Okay, so I need to set aside 2 bits for this. Okay, this 2 bits is because I need 2 bits to specify the 4 bytes. Okay, now the next thing is how many cache lines do I have? Okay, so I have a total of 16 cache lines, which is 2 to the power of 4. All right, so that means I need 4 bits to specify which cache line I'm referring to. Okay, 4 bits to specify which cache line, so I need 4 bits for that. So this is byte offset. Okay, this is the cache line. All right, and finally the remaining bits, okay, which will be 26 bits. This will be what we call the tag. Okay, so basically right now what will happen is whenever this 32-bit address goes out on the address bus, okay, goes on the address bus, I will need to extract out the byte offset, the cache line, and the tag. All right, and then from there, I will be able to check with the information that is currently in the cache to see whether there is a hit or a miss, and then take the next action. All right. So what will happen when there's a hit, when there's a miss? Okay, all these things is what we went through in the lecture. All right, so now let's go through the addresses that we have and see what happens. Okay, so right now what we have is we have a better idea of how we are going to decode the address, okay, from the address bus and map it to the different cache line or cache and figure out whether it's a hit or a miss. Okay, so since we know that the cache is initially empty, since we know that the cache is initially empty, that means you will always have that first stage of cold miss. All right, so the very first time I access it, all right, the valid bit will be not set, so I will need to update it with the fresh information and then set the valid bit. Okay, so that is the sort of compulsory or the cold miss that you will go through when you're first populating a cache. So let's look at the first access. The first access here is memory address 4. Okay, so what we need to do is you always need to translate it into binary. All right, that's why we have also given you the hexadecimal form, so it's easier for you to translate to binary. Okay, so let's look at the first address, which is 4. Okay, so for the 4, okay, all the first few bits will be 0. We know that the last few bits will be 1, 0, 0. Okay, it will be 4. So let me put in a few more bits. Okay, so we know the rest are all 0. Okay, now let's look at the byte cache line and tag. So the byte offset here, this is the byte offset, is byte 0. The next is the cache line. So cache line is the 4 bits over here. So this is the cache line and the rest is the tag. All right. So what will the cache do? So the first thing the cache will do is it will take this address information and extract out this cache line. Okay, this cache line, okay, is 4 bits, correct? That means total of 16 possible values, which relates back to the 16 different entries we can have at the cache. So now I'm referring to cache line 1. So I'm referring to this index 1. Okay, so initially, of course, everything is empty, so it is considered a miss. Alright, so the very first time I access this, it is empty, the valid bit is not set. Okay, so you supposed to have a valid bit over here as well. So originally the valid bit is 0. Okay, so in this case, what we will do is we will say it's a cold miss, and we will now have to update the cache with the correct values from this address. Okay, so what is the tag information? The tag information here is 0, so a value of 0 will come here. Okay, because this whole chunk here, this value is 0. All right, next is the bytes or the 4 bytes that I need to fill up here. Word 0 and word 1. Okay, so since all your data has to be aligned to the word, all right, so what you need to do is, since each cache line is taking 2 words, in this case it is 4 bytes of information. So when you say 4 bytes of information, it is always aligned to 4 byte boundary. Okay, that means let's look at it. Okay, if I say that I start from address 0, okay, if I start from address 0, then you can say it is 0, 0, 0, 0. Address 1 will be 0, 0, 0, 1. Address 2 will be 0, 0, 1, 0. Address 3 will be 0, 0, 1, 1. Let me just move it here. Okay, so with this, the next address will be 4. Sorry, this will be 0, 0, 1, 1. And then 4 will be 0, 1, 0, 0. So what you will observe is when I say it's aligned to 4 byte boundary, the last 2 bits will always be 0 as a starting point. So the last two bits will always be 00011011. Then again 00011011 and so on. Okay. So when I say I want to access the data from address 4, that means the 4 bytes, okay, that is part of address 4 will be 4, 5, 6, and 7. Okay. So this will be considered the information that we extract and put into the cache line. All right. So over here, what you will get is the contents of address 4 and address 5. And here will be the contents of address 6 and address 7. Okay, so that is the first thing that will happen. And since your cache has been updated, the valid bit will now be set to 1. All right, so that is the first access. Any questions on this so far? Okay, so it is the same steps that I'm doing that we saw in the lecture as well. All right, we extract out to first understand the cache design, and then once we know the number of bits for the byte, for the cache line, and for the tag, then we just relate that for every address that we come across. Okay, so now I'm just going to show you the first 4 access, okay, because the rest of it will take very long. So I'm just going to show you the first 4 access, and then from there we already will be able to look at the different sort of scenarios that can happen. Okay, so let me move this to the side here first. All right, so the next address access is 92. Okay, so 92 is hex 5C. Okay, it's hex 5C. So let me put it here. So it's 92. So in terms of hexadecimal, it's 5C. All right, so I'm going to, so 5C will be 1100, the last 4, and the 5 will be 0101. Okay, 5C, and then the rest will all be zeros. Okay, so similarly, we can extract out the byte information. Okay, the line information here, and then this will be the tag. And so this is the tag. So now it is pointing to line 7. Okay, this cache line 7, and again initially the valid bit is 0, so it is a call miss. So I need to update this with the information. So the first thing that we say is a tag. So the tag value here is a 1. So I'm going to put a value of 1 inside here. Okay, I'm going to put a value of 1 inside here, and then I am going to take the information. So in this case, as you can see, the starting byte is 0. All right. Okay. So in this case, it is the beginning of a 32-bit or 4-byte data. All right. So this is, maybe I should put here as 0x5c. Okay. So in this case, the data that I will be getting into my memory is memory of 0x5c, 0x5d, and here will be 0x5e and 0x5f. A, C, D, E, F. All right, so that is the second access. Now let's look at the third access. Okay, then we have something different. So in the third access, it is address 7. So if you look at address 7, 000 all the way 0, and then the last bit is 0111. Okay, the rest of the bits are all zeros. Okay, so if you look at it again here, you get the byte information here. Okay, and the line information here. and the rest is the tag. So what do you see? When it points to, in this address XS7, it points to line 1. Correct, line is 0001, which is this line. All right, and the tag is 0. Okay, the tag value here is 0, which matches the tag value that you see here as well. All right, so if the line that you're pointing to has a tag which is matching the tag that you have, and the valid bit is also set, that means it is considered a hit. So this is considered a hit. Okay, that means the data that you want is already in the cache. All right, the data that you want is already in the cache, and in this case, it is byte 3. Okay, 1 is 3, so this is byte 0, this is byte 1, this is byte 2, this is byte 3. So the byte 3 information, which is memory 7, is already in the cache, so I can directly take from the cache, and I don't need to go out to the main memory. Okay, so that is the this is where you get the advantage of the cache. Okay, because that now saves you that time and the hassle of going out to get the data and coming back in, because the data is already inside the cache. All right, now I'll just go through one more example. Okay, so again, this is a bit different, just to show you the boundary, the memory boundaries. So the next one is address 146. Okay, so 146 over here, it's hexadecimal 92. It's hexadecimal 92. So if you were to put it out in the binary, what you get is again 00 everything. So 92 will be 10010010. Okay, so let's look at it. So you have this as the byte, this as the line, okay, and the tag here. The rest of it is the tag. Okay, so this one is now pointing to line 4. Okay, so as you can see, line 4. So this one also should have updated to 1. Alright, so line 4 currently the valid bit would have been 0 because there is no access to it yet, and this is the first access to line 4. So in this case, I will now say this is a miss, so I'll update the information inside. So what is the tag? The tag value is 2. So a value of 2 will come here. Now, how about the memory content? Okay, so as you can see down here, this byte here is 10. It is not aligned to the 4-byte boundary. All right, so how do I know what is the content to take? So let's look back at the understanding just now of how we drew here. So if I take 90 hex 92, okay, so you can see that the last 2 bits, okay, if I just focus on the last on the second hexadecimal, it is 0010. All right, hex 92, the last, just focusing on the second hexadecimal, the least significant hexadecimal, is 0010. So this, as you can see, is not 00, it's not aligned to the 4-byte boundary. Okay, so what you need to do is you need to list down the next and the previous ones, and okay, so you can see that the data that you want 92 is actually byte, okay, byte 2, okay, from this 4-byte chunk. Okay, actually byte 2 from the 4-byte chunk, because we are always taking in terms of the 4 bytes. Okay, so the boundary is because of the need to make sure that every cache line in this case has to be 32 bytes. Sorry, 32 bits, that means 4 bytes. All right, and since our addresses all start from 0, that means the first boundary will be from 0 to 3, correct? Then 4 to 7 and so on. So the starting point of every uh, memory access that goes into the cache line has to be starting from the least 2 bits 00 and then go to 11. So that is why we have this 4-byte boundary that we need to align to. Okay, so when we are trying to access 92, 92 is actually part of the 4-byte chunk that is from 90 to 93. All right, so when I want to access this memory region and I realize there is a miss because it is not in the cache yet, when I populate the cache, okay, it has to be the data that is, okay, 90 hex 90, okay, 91, 92, and then 93. Okay, because you have to make sure that the data that you capture or you transfer from the main memory to the cache is aligned to the 4-byte boundary. Okay, why 4-byte? Again, because our data is all in, or each cache line is 32 bits or 4 bytes. So since each cache line is 4 byte and addresses start from address 0, so everything is going in that sequence of 0 to 3, 4 to 7, and so on. So if you look at the sequence, the last 2 bits in this case is always 0, 0. Okay, and the rest and the 4 byte starts from address 0, 0 with the last 2 bits. Okay, so that is basically how you do this question, correct? So the rest of it is actually the same thing. So I will not go through every step. When I release the solution, you can have a look. Okay, but as long as you understand the idea of how to populate this uh, cache by looking at the byte offset, the cache line, and the tag information, then I think that is good enough. All right. So let's look at the second question from the tutorial. So in the second question, basically, what you have is, yeah, so you are asked to um, come up with a structure, okay, for this cache design. All right, so in this cache design, basically what you will see is you have a word size of 32 bits and an address width of 32 bits and a 1024 block. That means in terms of the cache design, you have 1024 cache lines. All right, and each word is, each cache line has 2 words. Okay, so if I were to draw the cache, okay, if I were to draw the cache, okay, what you will see is I have a total of, okay, up to 0, 1 all the way to 1023. So 1024 cache lines, and each cache line has 2 words. Okay, this is word 0, word 1. Each of it is 32 bits. Okay, and the total here will be 64 bits. Okay, so that is how the cache is supposed to look like. Okay, in this. All right, now what you have to do in the first step is propose a C structure, okay, that will hold all the contents of the cache. All right, and you can assume that int holds a 4-byte quantity. All right, so again, why I put this int is because the one thing that is consistent in C is character. Okay, as long as you say character, all compilers will always allocate 1 byte for character. Okay, but integer is not a standard data type. All right, different compilers may interpret it differently. Okay, so that is why you should not use int in your code. Okay, generally what you should use is those standard data type definitions that is provided to you in some header file. or where they will sort of specify clearly whether it is 16 bits, 32 bits, or 64 bits, and so on. Okay, so in this case, I'm just giving you making it easier. So we say int holds a 4-byte quantity. So how can we come up with a C structure? Okay, so in this question, it is just to give you the idea of how you can sort of emulate cache operation in software. Okay, but of course, the actual design in the hardware is done using hardware description language. Okay, so if you have done modules where they teach you about HDL, okay, either Verilog or VHDL, that is what you will use to design such hardware blocks. Okay, but in this question, we are just trying to emulate that behavior in a C program. Okay, so in this case, okay, so this is one possible way in which you can do this. So if you look at the solution here, basically what you have is you have a structure where I've put in a valid bit, the address information, and a 2-byte data information here. Okay, so why I do it? So in this is not a direct mapping to how we have studied in the lecture notes, because I have not sort of broken up the address into the tag, the index, and so on. Okay, so I've just used the entire address to do a comparison to know whether the data is in the cache or not. Okay, so in terms of the structure, basically what you will have is you have a valid bit, you have address, and you have two sets of information. Okay, the two sets is because you have two words to store or two words you need to store for each cache line. All right, so it is a very simplistic approach, but just to get the idea of how it can be done. All right, so in the next question, I say write a function to find this or to see whether an address has a hit or a miss. Okay, if it is a hit, then you can return the value. If it is a miss, you can just say it's a miss and you don't need to do anything else after that. All right, so that is the idea. So in this example, basically what I do is I just go through the entire array. Okay, so this uh, sort of variable local cache would already have the entire array of this information, correct? That means this entire information here would already be stored, okay, inside my one data structure variable. So when I say find the address, what I need to do is I go through all the elements and I check whether there is a match. So when I do this, what am I doing? I'm trying to check whether it is a hit with my current address and the valid bit is set. All right, and at the same time, I also check whether I have a hit with the current address plus 4. Okay, plus 4 is to check for the next byte. So the next word. Okay, the reason why we need to do that is because we want to check for the word 0 and word 1. Okay, so since it is 4 bytes away, I sort of do that check over here. Okay, so there's two checks here. One is for the current address and the address 4 bytes away, and see whether the valid bit is also set. All right, so if it is either of this condition is true, then I say that the hit variable is a 1, and then I copy that information to a variable called the data, which I can then return back. Okay, if both of this condition is not met, then I say is a miss. All right, so it is just a simple example to show you the idea behind how this thing can work. Of course, it is a lot more detailed because you don't directly do a check with the full address, correct? You're supposed to extract out. Okay, based on how we have been doing it so far, we're supposed to extract out the tag and the line information and then know which byte to access and so on. All right, so this is just to give you the idea of how this whole thing is. All right, so that gives you some something you can relate to on the software aspect, right? So we understand the hardware side. So in the software side, we sort of understand how it will actually work. All right, so that sort of brings us to the end of the tutorial questions. Okay, so it's only 2 questions just to get a feel of the whole cache concept. Okay, now so that basically wraps up the entire module. Okay, so I will just uh, share one slide now to discuss on the exam related matters. Okay, so I will send an announcement on this as well to the rest of the class. Okay, so that everybody is aware. So the final exam, uh, the dates, please go and check the official the announcement or whatever information you get from the either office, SOC office, or from the registrar's office. Okay, so usually I do not discuss the actual date and time in class because sometimes things might change. All right, so just to avoid any miscommunication or something you hear wrongly and so on, I always leave it to the students to check the official information. Okay, so let me explain. So the first thing is it is Luminous Quiz. Okay, does anybody not have done Luminous Quiz before? Okay, but what I will do is just to make sure everybody is clear, I will create a demo practice quiz with just 1 or 2 uh, trial questions for you to have a feel in case you are not too familiar with how it works. All right, so that will give you some practice on how the whole thing works. All right, so it will be a Luminous based quiz, all right, with Zoom proctoring. Okay, so I'm not sure you've done it yet. Basically you'll be required to set up your phone, okay, your mobile phone, for us to do invigilation. All right, so that will allow us to sort of remotely monitor you. Okay, so the Zoom links and all we will send to you. All right, I mean I will send to you through the announcement and through the Luminous folders. All right, so what you are required to do is on your mobile phone you are required to log into the Zoom session and make sure that the handphone is connected to a wall power socket, okay, to make sure it is always powered up, and the positioning of the phone must be such that we can see you clearly, as well as uh, the one the angle of the screen must be such that we can see roughly what is that. Okay, we understand you can't really zoom in and see exactly what you're looking at, but at least we must have the sense that you are just focusing on the quiz and you're not trying to maybe open up some chat or something like that. All right, now it is an open book exam. That means you are free to access any class material that you have. Okay, it can be hard copy material or it can be soft copy material. Okay, but you're not allowed to access the internet. Okay, so to enforce that, what we do is we have the screen recording. Okay, so the screen recording is compulsory. All right, so you need to try out some screen recording software on your own, and at the same time I will send you all some sort of a preparation sheet on what you need to do, the timings and so on, and of course the some of the screen recording software that we have recommended to other students. Okay, generally I don't see any issues with screen recording for most students. The only thing that has sort of messed it up is when you run out of memory. All right, so it's good to have a trial run. Okay, that means one of the days while you're just working, just switch it on, run it for 2 hours, and just see how much memory it occupies. Okay, so I think in most cases it should occupy less than 1 gig. Okay, unless you have some settings that you go to very high resolution and things like that, then it will take a lot of memory. Okay, but in most cases, I think it takes less than 1 gig for about 2 hours of screen recording. Okay, but it's good to try it out on your own just to be sure and that everything is working fine. All right, so you can access any material that we have covered in class, which means your lecture material, tutorial material, and your lab material. Okay, but you're not allowed to have any internet access or any Google search or messaging and things like that. All right. Okay, all material will be covered. Okay, that means the entire module, everything will be covered. All right, where we will have both MCQ questions, all right, plus short answer questions. Okay, and you may have some analysis or writing of code. All right, so this is, of course, when I say writing of code, we do not expect you to remember the full syntax of uh, the OS, correct? Definitely the OS, if you look at the code, uh, you can have a lot of parameters and things like that. So we will simplify it. All right. So I will give you the instructions. All right. So for example, okay, you don't need to say OS mutex exactly how you want to create with a lot of parameters. No, you can just say OS mutex create and then you put a name. Okay, lock, you just put the mutex name alone. All right, so you don't need to put any additional parameters or things like that. So we will, when I ask the question, I will also specify how to use the OS functions in a simplified manner. All right, so you do not need to remember exactly which are the parameters, what is the format, and so on. Okay, so it will be a more simplified version of the code. Okay, analysis wise, basically, uh, like you may be given some sample code, all right, with task A, task B, like something like our tutorial question, correct? You have two tasks with semaphore, what will be printed out, right? So you need to analyze and then you need to see, okay, what would happen, which task will run, which task will get blocked, okay, and then what will be printed out. All right, so that is the analysis kind of thing. All right, so um, you can probably access the past year papers directly from Luminous. Okay, maybe I will show you. Okay, so if you go to Luminous, I think this is for all modules. If you go on the left hand side panel, if you scroll down, you'll see one option there under others as past exam papers. Okay, so if you click on that, you click on the module name, it will bring you to our NUS library, all right, and you can actually access the last paper. All right. So in this case, you have this one paper from 2018-19 SEM 2. Okay, so you can try this for all the modules. All right, you should be able to access the past year papers for each module that you're taking through the system. Okay, so that is basically about all that we have. Does anybody have any questions, anything you want to ask and clarify? Okay, the file size limit is more for your own safety in terms of making sure your laptop has enough space. All right. After you finish the recording, you will not be required to upload the recording, but you will be required to put it on some shared Google Drive or Dropbox or publish onto YouTube as unlisted video and upload the link. Okay, so I'll give you all these instructions. all right, on what to do. Okay, so basically you need to make sure the recording is there, but you won't upload the full recording. Okay, you will tell you what are the few options: either shared Google Drive, shared Dropbox folder, or upload as unlisted YouTube video, and then you will create a file to just give us the link. All right, so these links, of course, we will not go through each and every screen recording, but randomly the school will audit, all right, some screen recordings to check and see whether everything was done correctly. Okay, so I will prepare, okay, sort of SOP, okay, on what to do, what to prepare, and how the whole thing will run. All right, as long as you make sure you look at the correct date and time, and you log into the Zoom session, all right, then I think everything will be fine. Okay, so since open book, you don't need to memorize anything. Okay, you just can access all your material that you have. All right, but you are not allowed to have a secondary monitor. Okay, so that is one of the guidelines that we have to follow. Okay, because we have a second monitor, it's difficult for us to monitor what is really happening. All right, and just to avoid any unnecessary action. All right, so you must learn how to just manage everything within the space that you have on your current computer screen. Okay, so again, just for practice, I will release sort of sample practice quiz with just one or two questions, an MCQ, a simple short answer, and so on, just to have you just to make sure you have the idea and the feel of how it works. Okay, so any other questions? Does anybody have? Okay, all the folders for submission is already there. So once you're done, you can just submit. I've also sent you an announcement on how to name your file and to submit to those folders. Okay, so the deadline, again, take note of the deadline. I think it's 18 April, I believe. Okay, answer for past year paper. Okay, let me go through the past year paper first, and let me just see what, maybe one or two questions I may be able to release some answers. Okay, generally, I can give some guidelines on how to answer the questions, and maybe one or two questions I can give some answers. Okay, so that one let me go through first separately, and then I will send you an announcement on that. Okay. So any other questions? Okay, so the past year papers, let me check through first. Okay, and maybe I'll release some answers and guidelines on that. Okay, on how to answer them. Okay, so as I mentioned, I will release a document to give you the full overview on how the final exam will be conducted. All right, so that will give you some idea. So make sure that once I release that document, you go through it clearly. Okay, on your part, you need to make sure you have tested your screen recording software. All right, everything is there. Yeah, and make sure all your notes, everything you already have downloaded and kept it with you as a soft copy. Okay, on standby. And yeah, I think then you should be fine for the exam. Okay, assignment 2, I think is very similar to the tutorial discussions that we had. I mean, not the tutorial, I mean the sample files that I sent to you all that I discussed in terms of the message queue and task queue. So as long as you understand that and you look through the sample code that I send you, I think you can just very easily extend from there, okay, and do the assignment. Okay, so either using task queue or message queue, you should be able to do it. It is not compulsory to use semaphore or mutex, okay, unless you feel that there is a chance of some data corruption happening. Okay, so again, since it is an open-ended sort of question, each of you may use different approaches. So if you, the way you have designed your architecture or your software, if you feel that there is a chance that there can be some data corruption, if you do not protect any shared resource, then you are expected to use mutex to protect it. Okay? But if the way you design, there is no issue of that happening, okay, because you are explicitly sending and receiving data or something like that, then it's fine. Okay, the deadline, again, please check back on Luminous. I believe both the submission is 18th April, term paper as well as assignment 2. Okay, so for the term paper, I received some questions on how to draw the data part and things like that. So the data part and all, just you can use Microsoft PowerPoint, just draw some blocks, draw some arrows and things like that. If you want to use pen and paper and draw it out because it's easier and faster, it's also fine. But make sure that when you scan it or you take a photo of it, it's clear, okay, and I can see it clearly in the report. Okay, so for assignment 2, we're only dealing with integer arithmetic. There is no float involved. Okay, so you don't need to worry about float. Okay, the sample code for the assignment 2, you can refer to the sample code that I have uploaded, I think last week. Okay, so there's total of 3 sample code that I have uploaded. But one is on semaphore. No, one is the basic one, I think, and then there's one on the task queue. The other is on the message queue. Okay, so looking at task queue and message queue alone, I think that will give you either one should be enough to solve the assignment 2 question. Okay, so that's all I have. So thank you very much. Okay, for taking this module. Okay, I hope you have found it beneficial. All right, and yeah, so yeah, if you have other questions, you can email me first. All right, and then slowly I'll consolidate and probably send out an announcement just to make sure that whatever doubts that you all have about the exam or anything, I can clear one shot with the announcement to everybody. Okay, so you can think about it. All right, if you have other questions or any other things that you're still not sure about in terms of the exam or assignment or things like that, you can let me know, and then I'll consolidate everything in one announcement. Okay, so that's all I have. Thank you very much. Okay, have a good evening and all the best for your exams and for the rest of your degree program.